Great. Well, I hope nobody falls asleep here. Maybe I'll be the first one to go. Right. I'd like to first of all give you a little sense of my background. And I'd like to start and change the whole thing around because I'd like to have some lights for the audience because I really feel like I'd like to be able to see. Is that possible?
Boss says no.
Boss says no. Okay, so I'll just lecture into the dark here. What I want to do is I want to have it be very open, and anyone that has any questions at any point in time, ask it. My role normally is to persuade people, to educate people, share information with people. I do represent a vendor and I represent a product, but in coming down here today, I'm going to give you guys the straight line. Any questions you ask whatsoever, we'll go right into it. To give you a little sense of our company, that all sort of began in the early 70s in England. At that time, England conceived of itself as being a very socialistic country. And such, it embarked upon some very large computer programs to specifically develop applications for hospitals, schools. RUCAPS came out of that environment and has always been exclusively designed for the building industry. In 1975, it was used for the first time on a project which was the Riyadh University in Saudi Arabia. In 1977, GMW Computers was created for the purpose of selling systems to generate funds to continue developing the software. Okay, so that's real important because those early users in France and Belgium were the key to making RUCAPS a highly productive system. Their feedback was the essence of it. And user groups are tremendously important. We have a very unique user group situation in which a full one-third, a minimum of one-third of the fees that they pay to us for software maintenance go back into the user group, and they then direct how that money is spent by GMW, by us, in further developing and enhancing the product. So let's go on and let's talk about building modeling systems. We're going to talk about symbol and geometry in computer-aided architectural design. Talk a little bit about conceptual approaches to CAD, symbol and geometry, and then we'll of course focus on building modeling. My background is in architecture. I graduated from Washington State University, which is a much different sort of program than this. It was a very nuts and bolts oriented program, and I really like what you're doing down here. So basically, with respect to 2D computer-aided drafting, the approach is to essentially model drawings as a collection of pictures. There are a number of advantages to this. When we communicate architecturally, we're using an awful lot of symbols on drawings. The disadvantage, of course, is that people ultimately have to read those drawings and construct in their own mind what those drawings represent, which is a single object that we're designing, and that's a building. This is one of the primary things that GMW has been after from the very beginning, and that's the coordination of information related to a building. Okay. Now, when we talk about building modeling, we definitely do not mean solid modeling as opposed to 2D drafting. Building modeling is something which comprises solid modeling as well as modeling drawings. There are a number of advantages to solid modeling. You've got an actual object out there. You can cut sections through it. It's easy to understand. Some disadvantages with respect to the fact that as we communicate in the construction process, we use a lot of symbology to represent materials, for example. What we call hatching to represent concrete. All kinds of lines to represent steel, whatever the case might be. Now, typically, most systems have some kind of an approach with respect to the 2D, 3D relationship. They'll either take the 2D information and perhaps extrude it in plan view and from that create the 3D information, or they'll work the other way and create a 3D model, take pictures of it, and that then becomes your drawings. Now, we've gone into a whole different realm, which we actually pioneered and started by calling 2.5D, which isn't really a very good term for it. Box geometry is a term for it, and essentially what we're doing is we're taking flat images, 2D information, and coordinating that information into a single building model. This will get clearer as we go through the slides. Okay, Now, the building modeling approach is very different from the point of view that what we're actually doing is we're creating elements. The elements represent the components of the building. If we had the lights up and we could look around this wall, we'd have sheetrock, we'd have, you know, windows. All of these are elements that essentially we assemble in space. All right, that's the goal of this system. So we take components, we assemble them in buildings. All right, drawings for us, and this is the real difference. Drawings are something that we define. Just like you would talk to a draftsman, for example, I'd like you to draw the second floor of this building at a 1/4" scale. I'd like you to include all of the dimensions. I'd like you to include the space planning information. I don't want you to have any of the electrical wiring or that sort of a thing. So a drawing for us is a very simple thing that we just define. It's a little form that you fill out on the screen. We do not hold drawings in the memory of a computer. And this is a significant factor for us because we're able to put systems together with much less disk storage. Okay. Now, the advantages of this is that we get full automatic drawing coordination. We can virtually guarantee that every plan view, section view, elevation view, and all perspectives are 100% coordinated. And that's getting increasingly important as architects face tremendous problems these days with liability issues. Okay, so now we'll get into it and we'll start really talking about what we're doing here. I got the pointer. See how that works. There we go. Everybody can see that? All right, what I'd like you to notice, first of all, is that we're on the system and we're working now. This is what you would have on the screen in front of you. We're in a little program called Sketch. You'll notice in the upper box that it says Component Sketching. It's a component, it's window 12F. This is a plan view of this component. RUCAPS is intelligent enough to know which representation of the object you're interested in. And at this point, it's functioning essentially as any 2D drafting system would. We're composing lines, we're composing a representation of a window. If we were to literally take a section cut through that window at some height off the floor, that would not necessarily be what that window would look like. This is just a symbolic representation of that window. Okay, so we develop these components and then we assemble them into a building model. We start out here, we've got a model that's being developed. It's got some columns, some grade beams, some slabs. We're now in a different program which is called assembly. This is where we actually pull the component up from our library and assemble it into the building model. Okay, so you just build this model up much like you build drawings up. And the normal mode of interaction is plan view. Okay. Now, you might notice, for example, the doors. The doors are a very interesting element because in plan view we show it open. We've got a graphic entity there which shows the arc. But if we show that same door in elevation, we're going to show it closed. And if we show it in perspective, maybe we want it open 45 degrees. Within RUCAPS, you have complete and total control of that. And the advantage of that essentially is that we have other systems that are translating information from the 2D into the 3D. Perhaps you would have to go in and edit the graphic entity there which represents the arc or the swing. You'll see that more as we go on. And then of course we can turn off the RUCAPS grid. This is an example of more symbolic information, dimensions. This is just a little test model that we've put together. What I want you to notice though is that it's not a drawing. If you look at the upper blue box on the left-hand side, you'll see it's RUCAPS version 9.5. We're now in version 16, so that sort of dates these for you. But we're in a building, GMWC01, and we're on level 4 of that building. And that's very, very important. All right. Now then, you could have stopped there, and oftentimes when you're going through the design process, a job will come into the office, you'll work on it in plan view, perhaps only, and it'll go away for 3 months. But at any point in time that you want, you can go back into those components and add information related to other views of the same components. In this case now, we've added the elevational information of that window component, and that's linked directly to the plan view. You'll notice that we're back in component sketching. We've got the same component, window 12F, but this is view elevation XX. And that's what we mean by box geometry. Okay, so that we're taking this entity and we're placing it at some point, and depending upon whether we're looking at it in plan or elevation or cutting a section through it, we're going to have the appropriate representation of that object, the representation that we want in our contract documents. And that representation is entirely different than the geometric representation which builds up the 3D model. All right, so this kind of a view then, which is an elevational section cut of a model, was not drawn by a person, but rather this is the result of querying the system. In other words, you go out and you ask the computer to draw this for you. It knows the locations of those elements because you've already assembled them in plan. Is that clear? Any questions? Okay. Now, there's the door again. And in this case, the door is shown closed. We have another graphic entity which represents the swing. But you've only defined that door one time and handed it in the assembly process, and it's handed in the elevational view, fully coordinated with that plan view. Okay? Now then, we get to the geometry. Same component, window 12F, but it's defined in an entirely different manner. If we wished, we could actually now go in and cut a section through this at some specific point and show the mullions and the muntins, whatever the case might be. Anywhere along there we wanted, we could cut a section of it. This is the geometric information as opposed to the symbolic information which goes into the contract documents. And the result is, from our building model, if we wish to view it in perspective, or axonometric, or isometric, over 20 different kinds of perspectives, as a matter of fact. You can hold the vertical lines vertical, rather than having a third vanishing point. You can cut two sections through it at the same time on any angle. That's a tremendous advantage. We've successfully worked with contractors to build models of concrete frames and been a tremendous aid to the contractors in terms of actually getting the building built. But again, this representation is coming from your source, single point of information, which is your building, held in the memory of a computer. Okay, this is an interior view. And much like the way a 2D drafting system works in terms of layering, it's a very subtle difference, but we actually use categories so that each one of these elements belongs to a family. And by turning categories on or off, which is the same thing you do when you're talking to a person, you're saying, well, I want you to draw, you know, the fourth floor plan at a 1/4" scale, but I want you to show the space planning information and not the electrical wiring. By turning categories on or off, we can select what information it is that we want to see. Now, I want you to notice a couple things here. This room has a couple of plants in it, okay? And you can see where those plants are located here in the 3D representation. In the 2D plan representation, you can see the same two plants located in plan view. Okay, it's an entity, it's a component. It's been placed into that position in the building model. Now, what you're going to see here is something that you won't see any other system do. Okay? Excuse me for pushing this system, but I really think it's where it's at, and it's got the right kind of concept, and this is the direction we've all got to go. What we've essentially done here is we've answered a few questions. We've hit a little button on our digitizer board, and we said we want to go into elevation. We want to cut a section through here. And it says, fine, where do you want your section line? We identify 2 points, and those 2 points then create where you're going to cut the section and how long the section is. All right? Then it'll ask you, what's your depth of view? And depending upon whether you go on this side of that yellow line or on the other side of the yellow line, it then draws that little arrow because it knows what direction you're looking. But in addition to that, it comes up and it asks you this question, lower height, upper height. This particular project was built in metric units. The answer means, I want you to search for all of the information within this rectangular box in the building, except I want you to search from 24 millimeters below my floor plane to 4,500 millimeters above my floor plane. It asks you, is this okay? And you say yes. The result is, the system then goes out, finds all of those components in their correct location, and assembles them for you on the screen. All right, one of the things that you'll notice is that there are no hidden lines removed in this view. The reason is so that we can get that image up onto the screen as fast as possible so that it does not actually have to calculate obscuration, what we call obscuration. However, when you plot the drawings, it will calculate the obscuration and hide the information which is behind elements. Okay. Now, the beauty of this is that you can go into that model and work in elevation as well. In this case, we've identified our potted plant, we've picked it up, we're moving it, we're setting it back down, All right? And because we're working in 2 dimensions, in this case it's the x-axis and the z-axis, it'll stay on that plane unless we actually shift it back from that plane or shift it forward. If you shift it forward, it might leave the view if it goes on the other side of the section cut, for example. Okay, you set that plant back down, and every subsequent view of this building model is going to reflect that. All drawings are going to reflect that. All perspectives are going to reflect that change. There's no taking information and passing it from one file and converting it over into another file. It's one database. All changes made to one database.
Do you get that perspective just by entering those symbols in the plan?
No.
You enter the symbols in the plan and get all the perspectives, the elevations, and everything just from that.
Well, what you had to do, you have to take and first of all create each component with the plan view symbol, okay, and then assemble it. Now, you would have no information in this perspective if you had not, in addition, defined the geometry of that component as well. So having defined the geometry, having assembled it, you can then go in and run a program which allows you to visualize it. Does that answer the question?
Yeah.
Okay. All right. So to talk a little bit about process, because that's what it's really about. It's not just about getting to where we've got a drawing. It's what we as architects do. It's making decisions. It's changing our mind. It's developing an idea. As the idea develops, we change it. The more that we develop the idea, the more that people can see it, the more they can feed back to us, the more we change it. So change becomes a real important part of our process. And that's something that we have really worked very hard at to get a lever on, because that's a way that we can really save time in the office. All right. Now, so essentially what we're saying here is that there are a couple of different approaches. One approach is to model the building. Another approach is to draft the building. All right. There are advantages and disadvantages of each one. Essentially, the way you can think of this is that what's happening in our industry right now is that as we develop this new technology, our approach is to say, all right, well, how are we doing things now? And then to mimic the way we're doing things now. When in fact what we actually have here because of computers is the opportunity to really reflect upon what it is that we're doing and develop a new approach. All right, this is very important. For example, when we began to design airplanes, all right, when men have always wanted to fly, and women of course, what we did was we strapped wings onto our arms and we ran off of hills by mimicking the way birds flew. All right, well, what we really learned was that that wasn't the way to fly. All right, it's the same thing now. We think that because we draft and we draw drawings all of the time, that that's what we've got to do. That's architecture. That's not architecture. Architecture is getting buildings built. It's about that single object, which so many different people are involved with in its creation. And there's so much coordination of information that has to take place in order to get that building built and use that building. Okay. So change becomes a key process as we move from initial design. This is an English version of what we would call, conceptual design, schematic design, design development, contract documentation, as-built drawings. Okay? At each process, we're changing information. We're adding more information. We're laying a sheet down. We're laying another sheet over it. We're copying it again. We're doing all kinds of work that is no longer necessary to do. Okay. So with respect to drawing and computer-aided drafting per se, what we're doing is we're just mimicking that process, and we're holding individual drawings and individual disk files. And if we make a change to the building, we then have to go out into each disk file and make the appropriate change. And there's as good a chance that the change will be made incorrectly or that it'll be forgotten. So what we do is we actually give you the ability to go into one file, which is your building model, make a simple change. All right, and that simple change can reflect thousands of changes on drawings. This is especially true in hospital design, for example. Very complex systems, full coordination with wall elevations is a critical element, and you can have literally hundreds of sheets of drawings at different scales with different information. And it turns out that well over half of our users are architects. The rest are building engineers and building owners. And of those architects, over half of them purchased RUCAPS because they're involved in hospital design. And they know what the value of coordination is. Okay, any questions? Now, that single project database has the additional advantage of not only fully coordinating your drawings, but all schedules and reports which come out of it are always up to date. As we're moving through the process, all of these changes are made to that single project database, so that the designers can be working on that project database, or if you're in an office where they split design and production, and then that whole model can literally be worked on by the production department. So there's no loss of information whatsoever. Exactly what the designer was thinking about is right there in front of the production people. And that's very important. All right. The other advantage of having that single project database is that all of the various disciplines can look into that and see the appropriate information. And I've got some examples of work that our users have done where they have accomplished this to a very high degree. We're going to, we're going to talk a little bit about performance expectations before we go into those examples. This is very important. I want you to focus on the top two lines here, because essentially what we're doing is we're comparing the traditional computer-aided drafting approach with the modeling approach. All right? And what we do is we look at various things that we're doing in office. Basically, we create new drawings. And, and I would propose that really the only new drawings that we really create are thumbnail sketches. From that point forward, we're drawing it again at a larger scale. We're making decisions. We're drawing it on flimsy. We're drawing it later on 1000H. Maybe later we're drawing it ink on mylar. Okay? But what we really spend most of our time doing, and you learn this more and more as you work with the building modeling system, is we're really revising information all of the time. All right? A modeling system like RUCAPS will draft as fast as a drafting system. It has to. All right? It's got to accomplish that at a basic level. But where you really see the difference is when it comes to revising drawings. And it's because it's just part of the structure of the software. When you start changing that information, you find a tremendous gain in productivity. And then you begin to realize that really you spend more time changing information than you do drawing new information. And then you begin to get a real sense of the fact that if you're, if you're putting torque onto a bolt, a drafting system has got you out here and a modeling system has got you out here, because of your power of being able to coordinate changes to that single building model. Is that clear? If it's not, I hope that it soon will be. One other thing I wanted to focus on. As an architect using this system, all right, I have no background in computer science per se, except just through experience. For me, the real benefit personally has been the bottom line, building coordination. That's been the pleasure for me, because my experience, I had experience in contracting, for example, or construction, and I sort of miss that feeling of, going into an office and drawing and not being directly involved in construction. But when you're working with the building modeling system, it's almost as if you are, because what you're really doing is you're building the building the way the building's going to be built in the memory of a computer before you build it on site. And of course, that allows you to avoid a lot of kinds of errors. Okay. The other thing that we find, for example, we're quite often tested, benchmarked is what it's called. And people will say, well, what I want you to do for this benchmark is I want you to completely reproduce this drawing and this perspective. Okay? And that's fine, but what we have found in the majority of cases when we do a benchmark like that is that we find all of the holes, all of the places where their drawings weren't coordinated, because it's like building a cardboard model. When you're building a cardboard model, you have to make more decisions than you do when you're just drawing it. Okay? You've got to resolve issues about the elevations, about the heights of things, about complex joints. The same thing is true with the building modeling system. All right. So this is an example of a fully coordinated project in which the architect and the engineers both worked on the RUCAPS building modeling system from 2 different offices. It's a site plan. Okay, and it's a big building. It's a shopping center. Within an hour, you can build this kind of information up and immediately go in and image it. And this just proves that they build shopping centers as poorly in England as they do here. Okay, but now this is amazing, actually, what this engineer has done, because now he's got this ability to present these systems in ways that are very powerful that you would never see, or very seldom see, traditional engineers do in this country. Take advantage of the screen graphics to show the various systems, and again, the goal is communication, to be able to talk about those systems, to understand them, to know that you can build them. Okay, but in RUCAPS, you can go in and cut a section of that system and look at it. The 2 white lines represent the ceiling planes. This is the longitudinal section If we look at the other section, the ceiling planes become clearer. Any change made here is automatically reflected here. And any change made here is automatically reflected here, and in addition, it's reflected here. The power of this is the ability for everyone to sit down and look at that and understand where you're at in the process, whether it's going to work. Now, I've been waiting a long time for this, and I was really pleased when I first saw these slides. Here we're actually looking at it into the space, and we've turned on certain categories which allow us to look at the walls, which allow us to look at the mechanical systems, but the category which represent the ceiling planes was turned off so that we could look through the ceiling into the plenum. There it is in color imaging. Same view. And then if you want, you go out onto site, and there it is in construction. That's where we're getting to where, you know, the goal is to model reality as closely as we possibly can. Okay, another example. This is a couple of our early users here in the United States. This is from a very talented architectural firm in Portland, Oregon, named Zimmer, Gunsel, Frasca. What they did originally was they leased a terminal from an engineering office in Seattle, Washington called Boyle, Christopherson & Shire. And over a distance of about 170 miles between Portland and Seattle, they were both able to work on the same project. Okay, this is a hospital building. It's the Oregon Health Sciences building. It's the Institute for Advanced Biomedical Research. There you can see the combination of the architect's work and the engineer's work. The categories that I'm referring to are displayed on the screen in different colors. So if you turn different categories on in a different drawing, you get different colors. Okay, and that again, that helps us to understand the information that we're working with. Okay, but the beauty of this, you know, it'll take me a little longer to draw up an air diffuser, for example, one time on the system. But having drawn it once, the real power is in being able to place it and repeat it all over the place. We have different kinds of components. We have standard components which are fixed in dimension. We have stretchable components in which one dimension can stretch any length that you want. We have multidimensional components in which you can take a box and set it down and say it's 20 feet long or 2 feet wide, 13 feet high, repeat it, you know, just sort of mass out a building real quick. Those are multidimensional components. And now, I'm very pleased to say we also have what we call parametric components. Unfortunately, I have no examples of that, but at the end of this, I will tell you a little bit more about it. We'll have some slides on it very soon. I've just seen my first actual, I've just seen it on the system for my first time last week, and they're tremendously exciting components. At any rate, having placed this in the building model, okay, if we go in and add the sectional information to those components, we can then cut a section through it. And in addition, we can look at the full 3D geometry. Now you can imagine, you know, you would never do a perspective like this in the first place if you had to draw it. But we only had to define the geometry of that diffuser one time. It goes out and reads the file, the building model file. It knows where it's located and it positions it for you in space. Okay, now this is a little different example. This is an example of an interpenetration study. Here we're looking in plan view in a building called Delta on level 0 of that building. Okay, and we're looking at a mechanical system. All right, now what we're going to do is we're going to look at it in section. Same system. All right, we're going to zoom in on it. Real easy to do, very fast. With the, you know, we use Tektronix terminals. They have their own graphics processors in them. They make this kind of work virtually instantaneous. It's absolutely amazing. You just go from a whole building right down into the minutest part of the detail, just like that. Okay, but what we've done here is we've requested a three-dimensional view of it, and we've turned on a little switch which is called interpenetrations. And what interpenetrations does is it determines any place within a building where two geometric objects are running into each other. It will calculate the interpenetration of those geometric objects and display them for you in a different color on the screen. All right, now that takes a little time. That's pretty intensive CPU processing. So for example, the way it would actually work in an office, if you're doing a very large building, at the end of the day, you would request, you might say, well, I want to look at all of my concrete, and I want to look at all of my high pressure steam, for the whole building. You know, maybe it's a 20-story building, huge building could be, and just let it process overnight. Come in the next morning. It might only take a couple hours for it to do it, but it could virtually take that long for it to calculate all of the interpenetrations. Your task then would be to come in and determine which of those interpenetrations are permissible and which of those interpenetrations are not permissible. And then you get into soft interpenetrations. For example, we need to have so much clearance in front of this valve because a person has to be able to get to it. All right, we model those as well. I don't have any examples, unfortunately. Okay, there is the same system corrected, looked at in Imager. All right. Now, this is a real good set of examples because this begins to give you a little bit more of a sense of process. This is, again, one of our users' work, and they've gone in very early, and they're using the tool in schematic design, and they've just gone in, they've used these multidimensional components, and they've positioned them on this site. Okay? But the beauty of it with these multidimensional components is that when you place it, you give it its height and its width, as well as its length. So that if you go in and you cut a section through that area of the building, it shows this kind of information to you. Now, this is different than the way we would normally draw it, but this is very much for schematic purposes. Okay. You could make a change here. It would be automatically reflected in the plan. Okay. And there is the same building, or urban environment in this case, where we've looked at our multidimensional components and they've been masked up. You'll notice, for example, the interpenetration. We have a blue trapezoid set down here in the foreground, and as it comes up and interpenetrates the horizontal ribbon window, you can see how it goes. You can zoom right in on that and begin studying that as appropriate. Okay? Notice the difference in the color changing? RUCAPS is intelligent enough that when you identify one of those components, you take that little crosshair there and you move it over to the red masses, and you say, well, I want to change the color of that. And you can interactively drive that color change right in front of you on the system because it understands all of the pixels on that screen in those positions are mapped to that component. Very fast, interactive. Look at it from a different side. Look at the whole site. And now, this is very interesting, and I have personally found that this is a tremendous lever for me. What you have the ability of doing is assembling information in your building model in a very schematic format. Okay? And then you can take your windows, which are maybe just single-line representations. You don't know exactly what they're going to look like from the outside, but you get them positioned in space. All right? You assemble them. You look at it. You study it. And then you start thinking about how you might detail it out. You then detail that component, go in and globally exchange the higher level detailed information for the lower level detailed information, and the whole building comes up in level of detail. Very powerful. There's all kinds of things you can do like that in terms of, you might, for example, start out, you're designing a hospital or something like that, or an apartment building. You might just have little modules which you're placing down there. You don't know exactly what the room configuration is going to be, but you know the size of it. All right, you start working it and you start looking at the massing of the whole building, and then at some point in time, as you begin defining the room more and more, you just run exchanges and exchange the new information for that module. You see, a component can be anything. A component could be a hinge, a screw. A component could be something that represents a whole module related to a building. A component could represent a whole building in terms of an urban study. Okay. You could then take and say, well, all of these type of rooms are going to have certain kind of graphics in them related to, you know, what type of window it is, what type of door, what the room number is, and just run exchange, and all of that information gets automatically added into the building model. Tremendous time saver. Okay, same building shown in plan. Turn on different categories, look at different information. And if you want then, in this particular case, you can turn on the categories to show all of the fluorescent lighting fixtures as opposed to the air supply system, if you ever had a reason to do that. Zoom down into the model, you have larger drawings. By defining a smaller area of the building to be output at a greater scale to the plotter, You therefore have a 1/4-inch plan instead of a 16th-inch plan. And it's fully coordinated with the 16th-inch plan. Go in and make a change to your building model, and everywhere that you've positioned your 1/4-inch drawings on the drawing sheets, everywhere that you've positioned your 16th-inch drawings on the drawing sheets are automatically updated. Very, very powerful. Okay, look at that same building in three-dimensional line form without color. Add color. Very nice way of presenting information to a client about his building. Very readable. Okay, you can go into the interiors, turn on all the categories related to the interior finishing, look at the plants. If you don't like that particular wall system, change its color. All right? Now, if you don't like the green chairs that are there, then you can drive those green chairs through a color change. RUCAPS is intelligent enough that it knows the various orientations of the components, it shades the appropriate surfaces, and even within that single component we can have multiple objects in it making up the geometry, which they themselves can have different colors. So that one chair has got a different color for the casters and the legs and the chair, the fabric. Okay, we'll just do a little switch here. This is a hospital environment, and this is a real good place to sort of focus on what one of the real advantages of building modeling is. Let me see if I can get this to work. Well, for example, look at the lighting fixture over the bed. Now, three-dimensionally, geometrically, that's the kind of representation we want. But when we look at that lighting fixture and plan, we use a symbol that an electrical contractor understands that that's what you mean. And when you look at that room in a hospital and you've got to elevate every one of those walls, you might then just have 4 lines which represent the outside profile of the object because you want to show its height. Okay? So whichever representation you as the architect need to use to communicate your intention, it's totally up to you. It's your choice. You have that complete freedom. Okay? We also have tools which will allow you to draw a representation in plan, for example, and then extrude it in plan or section or elevation and then modify it. All kinds of tools to assist you in terms of building up that geometry as quickly as possible. But if you were to take that light fixture and move it down 6 inches, it's going to be reflected in the drawing. If you moved it down 6 inches and over 6 inches, it's going to be reflected in the plan. Full coordination. That's a key element. You can also envision the power of this, the ability for you to go in and request a schedule. I want to know how many TVs there are going to be in this building. And unlike a drawing system where you have to go out there and perhaps, do a little working around because you've got that same TV shown in the 1/4-inch plan and the 16th-inch plan, within RUCAPS you just say, I want to know exactly how much I have. Oh, thank you. No, it's not. But I think I'm getting by fine without it. Scheduling is very easy to do because you're not requesting a schedule of information on drawings. You're requesting a schedule of information that you have in your building. Okay, and you find that those subtle differences become very important in the day-to-day use of a system. Okay, so we look at a gas station. There it is. Oh, I see. We look at this gas station. In this case, it's very important to know that from the cash register's point of view, you can see all of the pumps and you can see everybody that's getting gas and driving away without paying for their gas. That kind of information is also very important when you're doing urban design, because more and more as communities get involved with what we as designers are doing, it becomes important to be able to say that, yes, from Mrs. Jones's window, if this building goes up 60 stories, she's no longer going to have a view of the Puget Sound. Okay, and we were instrumental in some aspects of the design of Expo 86 in Vancouver, BC. We were hired by the city of Vancouver to model the environment. The developer had gone in and built a huge model. Right? But with the model, you can't get into it. You can't experience the urban context as if you were actually walking through it. And our study, we did a fly through it and everything. Our study revealed that the way they were designing it was destroying the view corridors to a major landmark. And as a result, they made significant changes to the layout. Move outside of it, back away from it, and then it gets built. And this is very appropriate for these kind of building systems. Because as you develop your library, and every time you build a component, it goes automatically into your library and you have it for use on all future projects. That gives you another lever. Okay, having defined that television, you never have to define it again. It's there for the, the office has a real library. It can really develop its standards. People come and use it in the same way that you draw that television in your hospital floor plans is the way it's going to be drawn by the computer every time. And this becomes very important from a quality control point of view. Okay, now I'm going to sort of start finishing up the slides here. And this is an example of Viaskis. And we're going to take a look at this in video here in a few minutes. We're very proud of this. We completed this about 6 months ago. We consider it a landmark. It's the largest building model, to our knowledge, that's ever been built. It had over 500,000 components in it. Okay, and it was sort of nice the way it was actually developed. It was developed over a 6-month period of time by a friend of mine named Jeff Findley. And he did it in off hours, after hours, because this was sort of his own little pet project. And actually took about 3 months to develop the design, spent about another 3 months actually creating the animation to it. But what we did was each image was generated within the computer electronically to a resolution of 4,000 by 4,000 dots. And rather than filming the image off of the screen and then tying it together in animation, it was dumped electronically onto tape so that we had the highest possible resolution. Now, unfortunately, when you go to slides and then you drop down to VHS format, you lose a lot of that quality. Okay, so this original 16mm films are a much higher level of quality, but you'll see the difference. That's why I include the slides, because the slides are much higher resolution, and I wanted you to see that. The landforms behind the building were also generated automatically on the system. And I was mentioning to the guys in the video room that there's a lot of dangers to doing this kind of architectural presentation. We'll talk about that a little bit. One of the dangers, for example, is that you may not like the colors that you see there. Okay, well, don't worry about the colors and don't worry about the design, because the issue is what we're doing with building models. And when you present information, you have to be very careful of what kind of designs you use. For example, we want to model the Roby house, but some people will come into the office and not like the Roby house, believe it or not. So you have to, when you're putting demonstrations on for people, you sort of have to pick very generic architecture, so that in this case you're not focusing on the architectural issues, but you're focusing on the issues of what the computer system is capable of doing for you. Okay. Stuck. The gentleman that developed it, Jeff, is very much a purist, and you could see that in his designs. I think what I'd like to do is to touch upon this issue of using videos as a presentation format in the architectural process a little bit more. I've actually gone into architectural firms and shown this, and some of them have just been absolutely delighted, and others have been absolutely horrified. And the reason why they're horrified is because we're so used to seeing wonderful computer graphics on TV and in the movies, and we're used to just tremendous visual presentations. Okay, so now as an architect, if you use a medium like this, you yourself have to become a bit of a movie designer. And we've learned some tricks. We've actually developed 3 of these movies now. The Viaskis is the 3rd. We've learned some tricks along the way, but we've got a long ways to go. You'll notice that one of the weaknesses in this is the fact we don't have any people there. And that really, that's a real important quality, those intangible elements. Those are the harder elements for computer systems to do. We have, for example, one of our users is in Perth, Australia, and they'll generate 3-dimensional line images and then go in and hand render on them to give that drawing of that image a much more humane quality, to contrast the freehand lines with the very hard lines. And, that's a technique that's wonderful. Oftentimes when people get involved with computer systems, and I know that this is true of me because I tend to be a bit of a perfectionist, you want to work it all the way down to that last little minute detail, and try to model the people. But it gets to be, you spend a lot of time getting that last level of perfection, where if you just go ahead and take it off the system and then finish it up by hand, you can save a lot of money, and not blow the profit that you've made by using this tool. Okay? So the use of these tools, a lot of issues about how you use these tools, how you manage these tools. The other thing I wanted to point out about this is that you're looking at those blinds, and the system is going through and it's calculating all of the information that you can see through the blinds. And that takes a little time. That's a big difference between the micro computer applications and the super minis. I think we're pretty much dedicated to always trying to bring the higher levels of computer applications to the architectural profession, and there's a lot to look forward to in terms of what's coming our way, in terms of massively parallel computers that'll speed up this kind of processing and give us the ability to walk through it and visualize it in real time. But we're not there yet. We've come a long ways. RUCAPS users originally were prepared to invest anywhere from $200,000 to $400,000, $600,000 to get these systems. And now with the advent of computer systems like the DEC Microvacs 1 and 2, we're able to put these kind of systems into offices for as little as $80,000. And that's very important. The ironic thing is that the majority of our users seem to break into a couple of different classes. They tend to be either the very large firms, which can sort of afford these things. But on the other hand, we have a high number of users which are small firms. We have a six-person outfit in Olympia, Washington, a 4-person outfit in Houston, Texas, a 20-man outfit in Portland, Oregon, as well as a 70-man outfit in Portland, Oregon. And these smaller companies have the ability to totally transform how they work. The partners get involved. They use the systems. And it makes a tremendous difference because what you're doing is you're taking very talented, skillful people and you're giving them a whole new set of skills and tools to work with. And then what you learn as you work with computers feeds back into how you approach architecture in a very positive way, because it's just another thinking process, and you begin to learn what debugging is about. It's a tremendous personal growth. Okay. Now this is sort of my formal end of the presentation, but what I'd like to do, I've got some other slides that I'd like to show you, and if one of the gentlemen could go to the carousel, they'll notice that if they skip ahead, I can probably, or just go ahead and skip it ahead to that middle section of slides. I just got a few examples that I'd like to show you. Stuck again? Oh, well, that's all right. Yeah, that's the sure way to get there. There we go. That's what I wanted to show you. This is that 20-man firm in Portland, Oregon. Another example of schematic studies. In this case, there's no hidden line removal taking place, so that you can process it very quickly. I was particularly happy with the results of this. I sat down with one of the designers, and we sort of worked out the trees, and you'll find that modeling trees and plants are one of the most difficult things to do. This system is very much designed to represent buildings, and does that better, I believe, than any other system in the world. Okay, but then when you get into representing trees, you can begin to get a sense of the limitations. But as symbolic representations, I felt that these were very good. Very good. And then what you have to sort of get a handle on is how much level of detail do you go to. For example, the tires in the car become a little bit more than perhaps what was actually needed here. But that was a very tremendous way of communicating the design concept to the developer. Because these people aren't trained like we are to read drawings. And so as a communication medium, it's a tremendous extension of our abilities. Okay, this is a typical RUCAPS workstation. In this case, we're looking at a Tektronix. This is probably a 4115 terminal that has an image up on it. You'll notice the big horizontal table is an electronic digitizing board, so that wherever we move that puck on that table is fully coordinated with the model, the building model held in memory, or the drawing that you've got taped down. We have a very simple menu which is designed for architects. You can see the menu is sort of taped down, very simple, and it talks about things like, you know, elevations and sections and components, you know, creating lines and arcs. This is that example of that firm in Perth, Australia, where they've gone in and they've created the hardline image using the computer and then gone in and hand rendered over it. It gives it a much better sense of feel. Another interior image review, different colors, a little better than the original blue model that you looked at. Okay, we get a lot of work from English users, and they tend to model bars quite often, taverns, pubs. Okay, now, before we look at the esquisse, what I want to talk about a little bit are parametric components. Unfortunately, I don't have any examples. I'll just ask you to imagine this from what you've seen. You call up a component called stair, and it comes up on the screen, and it asks you a question. What's your floor-to-floor height? You answer it. What's the thickness of the slabs? You answer it. How wide are the stairs? Okay. How high is the handrail? And it'll tell you what the minimum is and the maximum is based upon code. And these are about 7 questions for that particular example that I saw. After you've answered all of the questions, boom, it puts the stair into the building. It's calculated exactly what the tread heights have to be. Okay? Now there are systems that are out there that can do some things like this in drawing form, but in RUCAPS, you can then go in and cut a section of that stair. And the section view of that stair is fully coordinated with the plan view of that stair. And you can go in and look at it geometrically. Look at it in Imager. Now, where this is all really going is the fact that we're talking about modeling buildings and all of the kinds of things that we've dreamed about in terms of being able to, well, there's a firm, for example, right now that mathematically can go in on a little Apollo computer. They design theater spaces, all right, but they have a mathematical representation of their building. They don't have a graphical representation like RUCAPS has. But they can say, well, I want to sit in the 20th seat back, and I want to position a sound source on the stage. What will it sound like? And they put earphones on, and it will show them what it sounds like. Well, now I want to add some acoustic material to the ceiling over in this position, and listen to it again. And they'll know what it sounds like. So that's where we're getting with this, is to model buildings, to model the lighting, to model the energy, which is one of the things we're doing right now, is tying in a thermal energy analysis package. And you've got to be able to model it in the schematic design phase as well as in the construction documentation phase. So that's where we're really going, is in terms of continuing to improve our ability to represent reality. And that can do nothing but be a positive feedback for architects as they try to conceive and communicate about this single object which they're building, which is a building. Okay, so now would be a real good time for us to take a look at the esquisse. There we go. And I think that all of you might want to turn around and take a look at the rear monitor.
This is a short film.
This is a very short film. It's about 7 minutes, and there is little sound with it. However, we may not get the sound. All right. This is essentially Jeff Findley limiting his exposure here by claiming the fact that he is an architect, not a film producer. And what you're going to see is purely the three-dimensional geometric information. There we go.
I've designed a small resort hotel, which is located on the shores of the Mediterranean. Within a 6-month period, I took the developer's brief, designed and built a prototype of a scheme in its environment. As RUCAPS is a building modeling system, my frame of reference was sharply focused on the building, with the knowledge that the drawings which would be required could at any time be plotted, and more importantly, would be consistent, whether they were plans, elevations, sections, or even images. This collection of images clearly shows the visual with 5 architect intents for the site. Unlike two-dimensional drawings, or even static rendered perspectives or scale models. This This medium will transport you into an environment which does not yet exist. The word esquisse is one which the architectural profession has taken into its vocabulary to describe the initial concepts of a design. And that is what you are about to see, the esquisse.
Doesn't all have to be animated. That's more economical. The music, you have to be careful about selecting the music. Some of that I didn't care for very much. And again, the design, But an architect, on the other hand, presenting their building would do, you could do wonderful things with that kind of a medium in terms of fading in, showing exterior walls first, and then showing interior walls, and then showing mechanical systems, and presenting what's important about the design concept. And these are the kind of techniques which architects will be and are using now to help themselves win more work. Okay. Now the only other thing, I brought a little information here, which there's enough here for everybody to have one of each. There's just a little color brochure which shows some graphics and shows the essential concept in terms of the ability to work in section and elevation and the coordination issues. The other thing I brought for you is something that I personally like a lot. We don't really hand the other set out very much here in the States. It's more used in Europe. But it asks the essential question, what else can you do with a drawing versus what else can you do with a building model? And I remember very well at the system show, I got a little button from some group. I'm not sure who it was, and I think it said something to the effect of, we're more interested in decisions, not drawings. And I wore that during the system show, because I think that very much our company agrees with that philosophy. And really now drawings are getting to a point where they can be an automatic byproduct, which is sort of a shock for architects, because we've grown to put so much loving care and attention into our drawings. But now, you just kind of focus on putting the loving care and attention into the building, which is where it really belongs. And if you're like me, I can set up perspectives real well, but when it comes to drawing, my freehand drawing isn't exactly like the best renderers are out there, so I tended to fall right into computers. I love them. Are there any questions? Anything I can do? There's a lot of issues here. There's management issues. A very important issue, which we haven't even touched on, is the issue of information sciences. What you name components, what you name drawings, so that you can retrieve it. There's tremendous implications in using these kind of systems, and offices have all kinds of challenges when they begin integrating these systems into their offices. And I'd be happy to deal with any set of issues that any of you have.
Ken, let me suggest that we go ahead with the panel session. I've structured a set of questions that might help answer some things and some other issues.
Great.
So why don't we go into that?
Sounds
good. If there are any other questions afterwards, people can have some time to answer.
Perfect. Sounds great.
Tom, Michelle, come up here.
Thank you.
They tell me that we're supposed to try and look into the camera back there when we're speaking, so don't be paranoid about it, but if you want to, you can.
Somehow I prefer to look at people.
Okay. Well, that's in the right direction anyway. First of all, let me point out that we have a rich background here in the area of CAD. Tom Cavan on the end here is with the Computer-Aided Design Group and has worked with a lot of firms around the country implementing CAD systems, and spent a lot of time investigating other systems out there. And Ched, I know, has been involved. Ched is, again, a principal at the Computer-Aided Design Group also, and has spent some time actually developing a CAD system at one point. They're currently involved in facility management software, which I hope we can talk about. So I think we can get some good information out of these people, so we see what we can dredge up with these questions. First, let me ask, I'd like to discuss some of the disadvantages of this and other approaches to CAD. I mean, we've talked about how great it is, but let's try and look at some of the problems involved with using CAD. I mean, you all have a lot of experience with this, and anybody can take up from there. And you might know, Ken, you might have some specific problems you'd like to talk about with your system, but any other systems in general.
Well, I'll start off with mine, since I've been the one that's been sort of selling you on building modeling systems. I'll let you know what one of the disadvantages is. And that is that oftentimes it's real appropriate to draw a section. You know, whereas we have to sort of model the building to get the section out. So there's still very much a place for drawing. And you can draw with RUCAPS, but it's definitely structured more towards the modeling end of it and providing those kind of benefits. So, you know, to a very large extent in the design process, you're still going to work a lot with pencils and paper. So that's one, you know, it's real, it gets real subtle, but it can be a disadvantage at times.
Tom, you have spent a lot of time installing a number of different systems. Are there any particular disadvantages using CAD systems that you would like to address?
I think using a CAD system, you have to take an enormous dedication to the application. Once you start using a system, you've committed yourself to fully applying all of your work onto that system. Once you get into the mode of putting some of the work on and some of the work you still do by hand, you're in a very dangerous situation. You're trying to maintain two technologies, and it's very difficult to match the two together. So once you've crossed the line and start applying a CAD system, you've made a commitment and you have to carry it through. And that's probably where most architects fail, is that they start off and then they get cold feet and they start pulling back. And after that has occurred, it's pretty much guaranteed you're going to fail in your application. So it takes an enormous dedication to carry it through. The other major disadvantage I see is that the whole building industry is not geared towards computers. Our contractors still expect to receive drawings in a particular fashion. They expect to receive drawings on paper. They expect the drawings to look in a certain way, because that's what they can read quickly. Most of your contractors are not going to spend a lot of time trying to understand your drawing. They want to see information represented in a very standard fashion. And many computer systems can't do that very easily. So you're trapped in a more traditional building industry environment, trying to apply new technology. And while the technology is very elegant for doing three-dimensional representations, so you can show your client what the building looks like, you cannot very easily go to the contractor and say, build this. So you're often trapped in that quandary also.
Is that a fault of the construction industry, though? But, I mean, I think that after having seen his presentation for a client, this would be great to present to a client. And I can see the drawback where you have to go back to a blueprint. I'm wondering if that's just something that you just can't add on to the computers. Now give you blueprints that a contractor can read. Doesn't seem like a major hurdle that you can't jump.
The actual representation of ink on paper is not the hurdle. The hurdle is more what symbols you're using and what kinds of lines you can apply to the page. Simple CAD systems are very different from the system we saw this evening. And we need to realize that this is on one extreme of the spectrum of CAD systems. I think Jerry is more interested in CAD systems in general and the spectrum you're looking at. And many of the CAD systems you would try and apply to architecture find it very difficult to represent information in the standard fashion. For example, stippling for concrete is a very common thing that we do by hand. It's very fast to do by hand. Contractors find it necessary to differentiate the drawing. A lot of CAD systems can't do anything as simple as that. So you are trapped very often just by the limits of the computer technology. It's not just a matter of getting blueprints out, it's what's on that page. What does that look like?
Well, that's what I was referring to. Let's say for amongst architects, you know, we can just say, hey, this is concrete, and we all know what concrete looks like without having to stipple it down. And what I was wondering if maybe we could have a separate part of the RUCAPS that would actually do drawings for a contractor. You know, do these kind of drawings for clients and architects who can understand this type of drawing, and then when it actually comes to doing the working drawing and the construction drawings, put in another program or whatever it takes to do the drawings that the layman can understand, the contractor, whatever. I just don't see it that big a deal.
You're building a fairly elaborate image there. It is a big deal in computer science to be able to do such a thing, unfortunately. You're dealing with the realities of computer technology today.
So there's a gap then between the modeling stage and the construction drawing stage. What about before that, between the designing and the modeling? I mean, how close is that?
I think there's a major gap in the difference between a coordinated building model, as we've seen this evening, and the more traditional way that we represent information in architecture. As architects, we're trained to handle pencils and paper. We're trained to represent things on two-dimensional sheets of paper. We model things primarily in our mind by looking at a drawing and trying to extrapolate what's there. A lot of the technology that we are taught in school, and I use technology in a fairly liberal sense, in that whether it's watercolor washes or anything, that's technology to me. A lot of that technology has been very specifically contrived to match the very crude and specific media we have to the images we're trying to represent. As architects, therefore, we tend to build certain buildings that we can represent on paper in a certain way. An architect who uses color wash very often tends to build buildings which are slightly different to the architect who uses very hard pencil constantly and nothing else. So the media does actually intervene in the process. The computer technology is another media. You cannot mimic, as we were told this evening, you cannot mimic pencil and paper technology. You shouldn't be mimicking that with a computer. You should recognize it as being a different media. And what's happening is that, as in the old technology of pencil and paper, the drawings that we created contained an awful lot of assumptions. And this is something which wasn't pointed out, I think, in drawings this evening. For example, if you take a section in an architectural plan, say you're doing a floor plan of this room, as an architect, you normally take the elevation of the section about this height off the floor, a couple of feet off the floor, except where you go through windows, then you jack up the elevation, you go through the window, you drop it back down again. If you're going across the floor a couple of feet off the ground, you don't slice through all the chairs. That would make gibberish with the floor plan. You raise the level of the elevation, you start drawing all the little chairs in plan. So you're making a lot of assumptions, which you can do very liberally by hand. But when you start modeling things in a computer, you're limited by the very strict interpretation of the computer. The computer assumes if you're slicing it 2 feet off the ground, you're going to go through all the legs of all the chairs, which would make it totally unreadable for the contractor who has to lay the furniture out.
A good way to do a stippling pass.
Yeah, put bar stools down, take a section through. But there's a lot of assumptions that we make in drawing, which computers can't make very easily. And there's a lot of problems there, which...
Yeah, I'd like to add to that, actually, because that comes right back into that issue that I was discussing, which is the symbolic representation versus the geometric representation. You know, the example where you cut the section literally through the model, 24 inches off the floor plane, is a cut of geometric information. And what I perhaps could have spent a little more time focusing on is that what you're doing is you're assembling the kind of representation that you want to have on the drawing through this box geometry method. And the other thing I didn't allude to in our most recent enhancement, what we've started doing now is what we call plan view obscuration. So that we're at a point where you can put the tiling down on the floor, set the table in, take the plan view, the table obscures the tiling below, but the model has the tiling in it. And then if you move the table, the next time it'll process the obscuration of the table looking down to the tiling below. So Thomas is absolutely right. It's a very complex, sophisticated set of issues. And you get into some real sticklers sometimes. I watched a friend go through a real painful learning experience trying to get the elevations coordinated because he had a conception of how he thought that the computer should work. I mean, this is very simple. We just cut a section through here, we draw these lines like this. That's the way we do it on paper. But the computer is a very different kind of representation of a building. It doesn't really understand that this is a building. It doesn't, you know, it's not like our conception of how we model an object in space. You have to give it all the rules. It's very precisely defined.
Let's, we got 8 more questions. I've got one more specific question regarding the RUCAPS system, then we'll ask more general questions. Word has it that the RUCAPS system, the people who developed it were also involved in the development of the GDS-BDS system, which was bought by McDonnell Douglas. And the same kind of thinking went into both systems. I'm curious if anyone has any information regarding that, and if the two systems are similar.
Well, that's a very good question. There's a lot of history there, which I'm privy to some of it, not all of it. Dr. Davison, who is the international director of our company, is friends, very good friends, with the people at ARC that originally developed BDS and GDS and Medusa also. And BDS, the building description system, is very similar to the way RUCAPS works in many extents. There are some major differences, as in my understanding, and you have experience with BDS and GDS. My understanding of BDS is that it also is a box geometry modeler, but we learned some things from BDS. I believe that you had to input all views of each object in order to use it, and we learned from that. We found that it wasn't necessary. You didn't always want to have all views in. You may only want a plan view in on some components, a plan and a section on other components, a plan and an elevation on other components, a plan section and an elevation on some components, and with some components, plan, section, elevation, and section. So we learned from BDS there, and one of the key differences is that we've linked fully together the three-dimensional side with the two-dimensional side. The limitations of the three-dimensional work became quite apparent, and I believe GDS was essentially developed as sort of a start over, now let's do a drafting system. So and I think that's essentially correct.
Yes.
The other thing that's sort of interesting that pains us a little bit is the offering of Medusa in the States, because Medusa is a fine system and is a very, very good solid modeler, and it's originally designed for, parts design and ship design, and now it's been brought here and is being represented as an architectural system. And what you find is there are significant differences between systems designed to handle land topography and systems that are designed to support the mechanical design process, and systems that are designed to support the architectural design process. And Thomas, I'm sure, could expand upon that better than I can, because it has to do with, sort of the hard coding of the data structures and how you represent the information. It's tremendously challenging. You can't have one system that's good for the architectural design process and the highway design process, and it's really tough.
I think that's true of all the systems that I believe, Tom, you know a little better than I do, but this system and the GDS from McDonnell Douglas are really the only two that were designed with architecture in mind as the first use of the system. Intergraph was designed for mapping, and the data structure is similar enough to architecture that there's a fairly good transition, but most of the other drafting systems were designed for mechanical parts design, and they have a very difficult time doing many of the simple things that we want an architectural drawing system to do. I think with this kind of ties together, because the representation that came up and the thinking that came out of England that you alluded to was all tied to systems building, so that when you went to the trouble of specifying a component so that it could be read from all the different views, you wanted to be able to use those components over and over again. Well, if that was tied into a system building methodology where you had a defined kit of parts, as it was with the hospital systems in England, then everything works together. You're only playing with a Tinker Toy set of 700 or 800 components. You can specify them once in the system and then design all different kinds and forms of building out of it. Now, there were a lot of problems, unluckily, with the systems approach in England at that time, the way it was financed, construction techniques, some of the basic premises of the system components that were done, so that the whole thing got a pretty good black eye. But I still believe that that's a really promising approach to architectural design. And if you look at things like gas station layout or restaurant chains or anything that's a repetitive system in the environment, to take a systems building approach to it and to be able to account for different climatic conditions and work within a given vocabulary, I really think could produce a lot better instances of buildings, as long as that's being brought about for a commercial purpose. There's a lot of economic reasons that has to be done anyway. And then the computer really starts to support that process, because it does start to tie the whole building process from conceptual design through to maintenance of the building together.
Right, that's exactly right. But probably the hardest thing you would ever do on RUCAPS is the design of a single-family custom home. Tough. really tough. But on the other extreme, in my experience at least, these systems, that work is worth it when you're dealing with really complex buildings, because your ability to handle complexity now is greatly increased. And so to a certain extent, it will allow us to design more complex buildings, because now we can represent the geometry more easily through the use of a computer than we could with traditional drafting techniques. And that's a very exciting part of it.
The computer-aided design group initially was involved with consulting to architects, and I think they are kind of moving out of that, or have moved out of that in the software development. But I'd like to ask, in their experience as consultants, in reviewing systems for clients, what sort of things do you look for in reviewing a system?
Well, Tom developed a really extensive checklist, so he's the one that
I get to monopolize the table.
Just the most important issues, I guess. Don't go through the whole checklist.
The checklist was about 85 pages long.
Seriously?
Yes.
Wow.
The most important aspect, I think, in any architectural system is flexibility. As has been mentioned, many systems which are offered on the market today were designed and marketed initially to other disciplines: industrial engineers, mechanical engineers, electronics engineers. It was thought 15 years ago that a line was a line, and putting a line on a page was as much as you had to do. All an architect did was apply ink to a page. And if you could get a system that could apply ink to a page, that was all that needed to happen. It fairly rapidly came to people's realization that an architect requires a lot more flexibility in the creation of line images than most other disciplines. I think the most powerful kit, component in any architect's kit, in the traditional kit, is the eraser shield. And it's so powerful that architectural drawings are very flexible. You can erase anything on the page at any moment, and you can change it and recreate it. And you can change the drawing very rapidly. A straight line quickly becomes a curved line. That's the most important thing to look at in any computer system, is flexibility. The ability to undo something you've done and change the design, change the image. So look for something which is equivalent to an eraser shield that allows you to take something out and replace it with something else. And I think that's probably the most important feature.
That kind of leads to a question about how architects view the coming of computers into their offices practice. What are the major objections that architects have to using computers in your experience? There's obviously a lot of resistance.
You mean once they've tried it, or just standing on the outside?
Standing on the outside, I think.
Well, there's capital investment. Architects don't have much money to spend. Workload goes up and down, so if you've got a lot of money tied up in equipment with a monthly loan payment you're making on it, you can't lay off the equipment like you can lay off all your staff, which happens every so many years in our profession. So there's a big problem. I think even, at $80,000 for a system, you're still not touching the average AIA-sized firm, which I think is a little less than 3 people. It's a major investment for them. And then there's all the general population's fears of computers. I think, you get into a whole grab bag of fears of misconceptions about computers and what they mean and the interaction with them, loss of creativity, a lot of misunderstandings about what computers can do. People seem to very seldom hit right on what computers can do. They either way overestimate the capabilities, like looking at a CAD system and thinking that when it's in a computer, all the intelligence that we read into a drawing, a computer can also read into, which is way overestimating it. And on the other hand, way underestimating some of the capabilities too. I'm sure everybody can add to that list. But.
Well, yeah, definitely. One of the things I would add is that the traditional structure is that the people that are making the decisions about how the money is going to be spent are quite often not the same people that will be using the system. So if you're a principal of a firm, there's a couple of partners or something like that, what you have is a situation you're going to bring in equipment and you're going to have to train an employee to use it. You yourself aren't going to use it. You have a tremendous investment in that employee. Tremendous investment in that employee. And that employee can then leave you and go somewhere else, and you've got to train someone else. And that's very expensive. So there's a fear there.
I think the most successful implementations I've ever seen of computers in an architect's office is where the principals have taken a complete commitment to the system and actually install terminals in their own offices. And they do the sketch designs on the system. And they pass the drawings around on the system. And they literally get rid of a lot of the paper. And those systems turn out to be very, very successful implementations. But it takes an enormous commitment on someone's part to do that. It means that you're redefining the structure of a typical office. You're no longer the principal who's going out marketing and just telephoning in the orders and say, give me a 20-story building by tomorrow morning. You're back in the office and designing on the system again and leading the way. You're showing people that you can use the system creatively and effectively. And there aren't too many offices that can undergo that sort of structural change effectively.
I'm interested in how the use of these systems, architects who are using them, designers who are using them, what are some of the more subtle effects that it is having on actually how a designer does what he does? Anybody comment on that?
Tom alluded to it a little bit, and that the media allows you to represent certain kinds of buildings. You left out airbrushes, which is my favorite one, and all the buildings that were done in the 30s that reflect airbrush renderings. And you had to figure out how to get the lighting to work so that the buildings could look like the renderings. I really think that that was a real strong medium. But I don't know, it seems to me, and I have not had a lot of experience in watching designers work with it, but it seems like designers can get trapped in some of the details because they're able to represent the building in more detail quickly in the process. And they get bogged down a little bit more quickly in working out the details. And it's harder to stay backed off to a more schematic level of design that you would do with charcoal pencils or just scribbling around with bubble diagrams and stuff, if you're on the system to do the sketch designs and stuff. But I don't know, maybe you too.
Well, there are a lot of issues there. I've alluded to a few of them. You begin to get focused on different set of issues. Certainly, one of the advantages of, for example, of using something like a building modeling system over pin bar drafting is you get real focused in pin bar drafting on the management of layers. And one of the things that I've really enjoyed about working with the system is the fact that you're back in focusing on the building, the elements that are going into the building, that are comprising the building, the way that elements come together and join in space. I think that's a very, very powerful improvement. Then on the other hand, you also find that you'll have to focus on the management of your information in a way that you did not have to focus before. How are you going to recall that information and reuse it? How are you going to design components so that they sort of have a generic representation that can be used in a number of different projects? And certainly one of the dangers is the fact that you can get real detailed and get lost.
Okay, let's move on to facility management. Chad and Tom are involved in developing something called facility management software. And first, just what is facility management, and where does CAD fit within that context? Chad, maybe you'd like to answer that.
We can answer that question. And we do it a lot every day. Well, I think facility management has become a real buzzword, and it's something that it's a new bandwagon that people are jumping on. And in some ways, it's not anything new at all. But it is the way we define it, it's a very broad definition and encompasses the whole building process. And that would include everything that an architecture firm does, as well as what people do in the early stages of analyzing the need for a facility, and mostly the operation and ongoing remodeling and refurbishing of a facility over its whole life cycle. The drafting system fits in quite a few places in that process. It fits in the traditional architecture sense, in just the way we saw the presentation tonight. But that information then can carry over into the operation of the building, and that's a little different. The graphic representation, when you're running a building, you're doing different things with the information. No longer are you trying to rapidly produce a set of drawings to build the building, but you're more trying to use the information to be able to go in and extract or query it like you would a database. So you might want to go in and say something like, show me everywhere there's vacant space over 2,000 square feet in area, but less than 4,000 square feet. Oh, okay, it's all those areas. Well, who are all of the groups that bound any side of those vacant space, and where are all their locations in the building, so that you can identify groups that you might be able to move in order to free up enough space to move a new department in. Those kinds of activities, or show me every room that has available electrical outlets or unused air handling capacity, to be able to find a new location to put some equipment. And then normal inventory functions and costing out of reports, trying to charge back the amount of space that different groups occupy or manage leases. And there's a lot of reasons to represent that information in graphic as well as alphanumeric form, but you're not doing much manipulation of the graphics in a lot of that. You're just retrieving information and looking at it. And a well-organized drawer full of drawings might serve pretty well a lot of those functions. It depends on how rapidly the data turns over, the change rate of the facility. But with the cost of facilities going up, there is more motivation to put it on computers. And there are also, the way large companies are organized, there's a lot of reason for multiple departments or divisions within a company to have access to that same information, a common database. And just like they're talking about a common database in the design process for all the different disciplines to be able to tap and get the same information, that same thing holds true in facility management for the different departments, personnel, finance, purchasing, that relate to keeping the facility going. And I give that answer a lot every time.
That's right.
Try to do a little different variation on it each time.
Well, and you related one of the items in there that is an advantage to a building modeling system, which is that the information or the combination of information on a drawing which is required by a facilities manager is oftentimes different than that required by the contractor to build the building. So the advantage of a building modeling system in that case is that having fully represented your building, if at some point in time the owner needs a drawing which shows the representation of the air supply as opposed to the fluorescent lighting fixtures, he need only request it. So that the information is there. You've got an ability to query a database, which is your building, as opposed to a set of drawings, which aren't a building, they're a collection of pictures. And that can be a real tremendous benefit for the relationship between facilities management and computer-aided design.
I think just like one way of writing off the cost of doing a drafting system is to be able to use the information over many designs. Another way to write it off is to be able to use the information over a long period of time within the same building. And you can justify spending a lot more effort in building a good model of the building if you're going to be using that model either across a lot of projects or over a long period of time or both.
That's right. And developers and clients are people oftentimes that are more familiar with the use of computers because of accounting or whatever the case might be than architects are. And they literally are beginning to demand that their architects put their projects onto CAD. And that's probably the major reason why there's been an increasing thrust in acquiring this kind of equipment in offices. I know personally of developers that just literally won't use an architect because what they want is an architect that will give them the tape back at the end of the job, and certainly the government is a good example, which brings up a whole new subject, which is compatibility and the international graphics exchange standards and whatnot. Very complex set of issues.
Tom, did you have anything to add to facility management?
Not much to say after that.
Okay, we got 2 more questions left. I think one of these Tom will have something to say about. With the advent of artificial intelligence and expert systems, I'm curious about how that's going to impact the design process. I think it's quite likely that at least some portion of the design process will be automatable, and if not automated. And I'm curious to what degree this is going to impact what we do as architects. I want to ask Tom a question. This question about expert systems, and he told me that he didn't think there would be any expert systems in architecture, or intelligent systems in architecture until there were some intelligent architects. And I later asked him to elaborate on that, and I'm kind of putting him on the spot right now. I'm going to let him speak on that if he wants to. He doesn't have to, but I thought there were some real good answers that he gave. You're up to it, Tom.
Well, since you put me on the spot, I'll just go further out. I'll hang myself completely. I do believe very strongly that the whole issue of artificial intelligence in architecture today is a red herring. I really don't believe that most architects understand what they're up to. We're trained as architects in a craftsman tradition. And the essence of the craftsman tradition is obfuscation. It isn't clarification. We tend, in the architectural training process, to cover up most of what we're doing. And in fact, we don't need to understand what we do most of the time in the business. In artificial intelligence systems, at the moment, are highly specific. They address very particular issues. And I don't believe that architecture as yet has got itself down to the science of addressing particular issues. Each building tends to be a crafted object still. And architects love to redesign handrails. They love to redesign the doorknobs. They love to redesign the staircase. Even though everyone does that constantly, day in, day out, there's this urge to redo it. And there's not that much in architecture today which lends itself to highly intelligent systems in the way that we understand intelligent systems in other disciplines. Intelligent systems are fine in oil drilling, where they're trying to check whether there is indeed oil underground and whether they should expend the billions of dollars to go and drill down there, or should they find another way of rationalizing if there is anything there. But architecture isn't at that level. And my belief is that architects can get away quite well with charcoal pencils and pieces of paper, or computer systems which in some way allow them to model things in that fashion. But whether we need to start pushing towards artificial intelligence in architecture, I really don't believe that's the case at the moment. And that's why I came up with that quip about no intelligent architects. There's a truth in that.
Well, do you think architecture can survive in the craftsman tradition for much longer as a profession?
I believe it is going to survive in that tradition for quite a while longer. I don't believe that we're going to see it in the current form, that the whole profession is going to maintain its current form. But I don't believe that 95% of the profession, which is all of the offices under 5 people, is going to die out. And the offices in that range tend to be the craftsman tradition offices. Architects, I think, architecture is going to survive, but the whole definition of architects is going to change. And we're going to get into other areas. I think architects are surviving today by getting into land developing. They're surviving by getting into contracting and construction. And we're beginning to merge architecture with the other professions which surround us. The profession of architecture as we see it today, as delineated today, was actually only set up about 100 years ago by the French. And it was the whole French engineering tradition which evolved into the architectural tradition, which then proliferated itself around the world. And I don't believe that's a God-given fact. I don't believe we're frozen in that. It's an evolutionary process. And I'm getting a little bit off your subject about artificial intelligence here. But that's why I think architecture is an ill-defined profession. And that's why I don't think there's going to be artificial intelligence systems which address very particular issues. There are systems which address things which we might see as being artificial intelligence in some ways. We heard an example today of parametric objects, of being able to just answer a few questions and a staircase appears. That's artificial intelligence at the level of, I suppose a snail has intelligence. But it's a long way to the level where we would like to have artificial intelligence today.
I think, too, we'll see more application will come. The process of architecture is based upon this world of intangibility that you're referring to. Obfuscation, is that what you said? Very intangible. But as we define that building, a lot of rules can take place that are more related to the engineering professions. And I think that's where we'll see the introduction of artificial intelligence and expert systems first. Having defined a building, you know, it's a pretty standard, clear-cut set of rules, supposedly, with regards to the design of the HVAC system, or the lighting systems.
Yes, there are many systems on the market today which will assist you in designing an HVAC system.
Right. So there are places, it is happening, it is going to happen, but...
That's in the building profession rather than architecture.
In architecture, per se, that's correct. To the degree that an architect might specialize in a particular type of building and develop a particular expertise, the design of skilled nursing facilities or hospitals or gas stations, then as you developed an expertise in that building type and you began to understand the rules that you yourself applied, because there are definite rules that come out of codes, for example, you know, you'll see those kind of areas being applied or applying expert systems and artificial intelligence first. But on the other hand, you know, the architect themselves as a person will be at the pinnacle of the design process with respect to diversity. Okay, so that as we're designing different kinds of buildings, that, you know, and changing all the time, you know, do a house here, do something else here, you know, that's where the expert systems aren't going to be able to solve many of the issues and problems.
We've got about 10 minutes left on the tape, so let's ask the last question. And we've got about 6 minutes we can spend on that, and then maybe 5 minutes for any other questions that you might have. The last question is, it's been suggested that the needs of the practice of architecture and the needs of education in architecture are quite different. Most of the software that's been developed at this point has been developed for practice. My question is, what sort of software is appropriate for education? And how is it different from what we're seeing now? Ideas?
Well, this is a point that was raised at the Acadia conference. Yeah. I think it's a really interesting point. There's not much justification for companies to develop software for architects to use in the profession. And it's going to be more of an act of love to produce architectural software for training architects, I think, in terms of economic return on the effort. Schools might be able to do it. I know there's been some effort at UCLA when I was there to develop some training software, and Marino worked on some for teaching solar loading and sun patterns and those kinds of things. It would need to have an educational component. I think it's something to really explore. I've never really thought about it until you raised it last week. And, do you have any ideas for what kind of form that would take?
I think there's a very simple rule of thumb that you can use, in that you're trying to find software to help train architects. And you can look in a different field. When you come to architecture school, is the point of coming to architecture school to learn to use watercolor washes and airbrushes, or is it to come to design buildings? Should you get a computer software system which teaches you how to use computer software for pushing a pen around a page? Or should you get a computer software system which encourages you to think about architectural constructs? And that fairly clearly defines the two sides of the argument. A lot of architectural schools believe fairly strongly that you have to learn how to push a pen around. And they'll teach you engineering drafting, and they'll teach you how to draw on a CAD system. And there are other schools which will believe very strongly that you might have to learn to use an airbrush. So there are other schools which believe when they're using computer software, you shouldn't go anywhere near a drawing system, but that you should use conceptually challenging computer software, which makes you think as an architect of architectural constructs. Both sides have their arguments, and I think both sides have some rights to be heard.
What's an example of the second kind of software? What would the interaction with the student be?
I think the system you see at UCLA being used to teach architectural design is an example in that one, where students are taught programming. They're not taught how to use a CAD system at all, but they're taught almost immediately how to design parametric design. And they very quickly come through into three-dimensional color modeled and shaded images, which are parametrically designed building forms. and they understand how forms relate one to the other, but they have no concept of how to put a drawing together. They're talking about architectural sculpture in software. That's the other extreme.
Let me just close with this one extra question. For the people that we're talking to, the students primarily, how important is it that they come out of here with the knowledge of computers, and both in the short term and the long term, and what level of knowledge is necessary, is going to be necessary for them to be successful in the field?
Well, I think it sort of would be like asking a group in 1850 how important it is to know about machines, motors, or engines. It's something that's going to permeate our lives. It already has. It's going to be much more visible. I saw statistics the other day that there's 1 in 3 in 100 homes have a computer in it, and they expect that to be 33%, up from 3% in the next 4 years. So I think we're on the threshold of a real explosion of computers in every aspect of our life. I don't think it'll even peak in the time that we're alive, people in this room are alive, electronic revolution. So there's that level of understanding it as a major force in our society that, you know, will affect us no matter what we do. And most of us won't practice architecture if you look at the statistics of people that leave architecture school. So I think there is an important, you know, there's a very important thing to just knowing the basics about computers and understanding, not being intimidated by them, being able to relate to them, and understand what different software can do for you. Then you drop down to within architecture, and I don't want to keep the whole floor, so I'll stop here.
Well, I think you made some excellent points. My personal feeling is that the most important thing is just that you be open to it, and that you be, I mean, if possible, excited about it. You're going to have lots of opportunities in your future to be involved with it. Okay, and I think you really do only have to know the basics. I'm a perfect example of someone that doesn't know how to program. I don't think you have to know how to program it. It's nice to understand what's happening there, have some model in your mind of how it's working. But these systems are getting easier and easier to use all the time. And they're going to continue to get easier to use. And you're going to be able to just sit down and use them in the future. So I think while you're in school, stay open to it, learn what you can, focus on architecture, focus on the basic skills of thinking and communicating. I think that's the key.
Bill Mitchell, you know, in the paper he gave a year ago or so, made basically the same point. The idea of computer-aided design and things is almost over with, like we would talk about pencil-aided design. You don't say it that way. And it's going to become more and more just a fabric of the office. That's another tool like an airbrush that people won't be making such a big deal of. To some extent, like people, clients demanding that that drawings be on the computer is a little bit of the emperor's new clothes to me. They're not sure why, and in a lot of cases there's absolutely no point to it, but they're doing it for some reason. And I think that, you know, is just part of a new technology being introduced that will fade, hopefully, because it's not, the important thing is what the building is that comes out of the process, not the tools that we use to get there. We just want to be as efficient and do as little boring work as we have to.
We got 5 minutes of tape left. Any questions?
Yeah, this all sounds great. It's all exciting, but I have a question about the costs. From what you said, the cheapest one you have is $80,000. And I want to know, why is it that expensive? And is it because the market is not there yet? There are not enough people to manage it? Or is it the level of sophistication of this program that is making it cost such an outrageous amount of money?
Oh, there's so many issues there. Certainly the technology, the cost of the technology. I mean, we're fortunate. If it was not for the work that NASA has done and that the Defense Department has done and that the automobile industry has done, we wouldn't even have access to this kind of technology right now. You take a company like ours, which is dedicated to the architectural market, and boy, it's tough because it's not a big market, and it's really hard to put the work into developing these programs because there's hundreds of man-years in RUCAPS already. There's something like 570,000 lines of Fortran code that has to be managed and maintained. Now, it's a tremendous task. It's, I mean, we're bringing a lot here. There's a lot of work that's gone into it. And unless we could sell 1,000 installations in the course of a year, we couldn't possibly get the price down to, you know, the more of the micro CAD, $2,000 for a piece of software kind of price. It's just market demand and supply.
Is it possible, though, to lower the level of sophistication so that I can buy one for $10,000?
Certainly, certainly.
Then you can sell more.
That's right.
Eventually, I'll buy one for $30,000.
Mm-hmm.
But
Definitely.
you can buy a Volkswagen Bug for $8,000, but you wouldn't take the Volkswagen Bug and drive up to the top of the Himalayas because it wouldn't get you there. So you can certainly buy something within your price range, but you have to recognize what you're buying.
I don't go to the
Right?
That's right. So,
Right.
you know, don't complain about it being expensive to get up there.
Right, right. And the costs will keep coming down, especially with respect to hardware. And so as we move into our future, they're going to become more and more affordable. We're working very hard at that. We have to.
You have to recognize, actually, I was a little facetious before, but the costs are all relative. It's what you're trying to do with the system. And $80,000 might sound expensive to us sitting here because we couldn't afford to write out our own personal checkbooks. But on the other hand, $80,000 is pretty cheap when you've got $20 million in fees coming in on a project.
That's right. And
that's not unknown.
And when you're looking at the tremendous liability issues that face you, and these systems, you know, we're very much interested in this issue of coordination. You know, and $80,000 is not that great of an investment. And if you do get gains in productivity, which you do, these systems typically pay for themselves within a year or two in that approximate range. At least that's been our experience. So, I mean, you know, it's a question of making an investment. And the profession is not used to making an investment, as was alluded to before.
There weren't really any tools. I make this comment in my introduction class that the Industrial Revolution really didn't give us much except the parallel rule and electric pencil sharpener, and even that required electricity. But this revolution, since we are information processors, architects basically take information in one form and transform it into another form, from a verbal description of the building, plus building codes, rule structures from graphic standards, and we translate that into a set of lines, drawings that a contractor can read, as well as other aspects of modeling, hopefully. And so since a computer is an information processing tool, there's just a tremendous potential there. 80,000, a draftsman in an architect's office with overhead expenses and so forth would cost about $30,000, $40,000 a year. So if you gained a productivity, if you increased the drafting person's productivity, just using simple numbers, if they came out 2 to 1, produced twice as much work, it should pay for itself in 2 years or a little more.
That's exactly what I was thinking about. If you have a 3-man office, that's where they're going to need this most. That's where they're not going to afford it most.
They can afford it. It depends upon, it asks for a bit of ingenuity on the part of the people who finance systems and people who sell systems. That's what's lacking in the marketplace today. They don't need to come and ask for $80,000 in cash right now. They could ask for you for, you know, $500 a month for a certain number of years, or $2,000 a month for a certain number of years, and allow you to pay it slowly over time.
We're out of time now. We got about 30 seconds, so I'd just like to thank...
We can keep talking. It just won't be for posterity or for next week.
Let me thank Ken for his efforts here. Thank you very much. And thanks to Tom and Chet for coming. And we're able to dredge up a lot of really good information, I think. And you all get a free copy.